Hi, welcome to the next lecture on Haskell. In this lecture, we will look at a new concept. We have encountered this previously in passing, but we will actually look at it in detail in this lecture. Okay, so let's begin. So the topics we will be looking at is polymorphism and what are called type classes. We will see what these terms mean. Okay, so consider these functions. Length. Okay, length of empty list is 0. Length of x colon xs is 1 plus length of xs. Okay, so the point is that the x is not used at all, right? So it's just that it just contributes 1 to the length and that's it. You don't care what x is. Okay, and similarly, when you recursively call length of xs, none of the elements of xs will be used either. They will be used in the sense that each element contributes 1 to the length, but you don't care what the elements are. Right. So similarly, look at reverse. Reverse of empty list is empty list. Reverse of x colon xs is reverse of xs plus plus singleton list x. Once again, of course, here the x is used, but it doesn't matter what x is. Okay, this is the point. Here x is not even used, and you could actually have a more accurate mylength function where you indicate that you are not using x by saying mylength underscore colon xs equals 1 plus mylength xs. Right? Here x is used but not modified. Does not matter what x is. So we can say not used in an essential manner. Okay. Look at init, another function. Init of singleton list x is just the empty list. Init of x colon xs is x followed by init of xs. Here again, the point is that none of these functions look into the elements of the list. They might copy the element from the input to the output, or they might copy it into a different place, but they do not look into the elements of the list and do some modification based on them. In contrast, look at some function like sum. Sum of empty list is 0. Sum of x colon xs is x plus sum of x. Here, I need to know what the element is, or at least I need to know what the type of the element is, because I cannot, for instance, do sum of true, false, true. This is not accepted. Why? Because plus does not apply to booleans. Okay, so so these functions do not look into the elements of the list in a sense. To be more precise, they will work over lists of any type whatsoever. Okay, whereas sum, you might think of it as list A arrow A, but A has to be a numeric type. A has to be some type such that the function plus makes sense on elements of that type. Okay, whereas these will work over any lists of any type. Okay, there is a name for this that is called polymorphism. Okay, polymorphism. These are functions that work across multiple types, same computation. This is really computation rule, applies over multiple types. no difference in code at all. This is the important thing. There is no difference in the code depending on what elements you have to access. For instance, if I have to do reverse of 1, 2, 3, what will I do? I'll so this is reverse of that is nothing but reverse of 2 colon 3 plus plus singleton 1. This is nothing but reverse of this is nothing but reverse of 3 colon empty list plus plus singleton 1. Yeah, this is reverse of reverse of 3 colon empty list plus plus singleton list 2, the whole thing plus plus singleton list 1. And now if you expand this, this will be reverse of empty list plus plus singleton 3. Now you do plus plus singleton 2 on this. Now you do plus plus singleton 1 on this, and reverse of empty list is empty list, so you will get empty list plus plus singleton 3. Which will eventually give you 3 to 1. Fine, but suppose instead I want to do reverse of true, false, true. The computation is exactly similar, except that instead of 1 I will use true, instead of 2 I will use false, and instead of 3 I will use true, right. So, this is nothing but reverse of true colon false colon true colon empty list, that is nothing but reverse of false colon true colon empty list plus plus singleton true, and so on and so forth. You see that the computation rules are applied in precisely the same way, and it does not matter for the reverse function what the actual type of the elements is. So, the reverse function is polymorphic, okay. It works no matter, it works the same way over lists of integers or lists of booleans or list of characters or whatever. Okay, in such cases, what type will you give to the reverse function? You will use type variables to denote the flexibility. You will say reverse is a function of type list A arrow list A, right, or you might say fast reverse is of type list A arrow list A. Fast reverse might use reverse into as a subroutine. Fast reverse is nothing but reverse into the empty list, where, and you can give types to local functions also. Reverse into is of type list A arrow list A arrow list A, and then you say reverse into accumulator of empty list is accumulator, reverse into accumulator of x colon x's is reverse into x colon accumulator of x's, okay, fine, sure, but the point is that you can give these very general types, list A arrow list A arrow list A, list A arrow list A, etc. So, here A, B, C are placeholders for types. Sometimes you use T, etc. Sometimes GHCI itself uses T, T1, T2, etc. are also used. It does not matter, you can use anything, you can even, it is not necessary that you should only use letters, you can use even longer strings as the type variables, okay. Just like list integer denotes lists of lists whose elements are of type integer. Similarly, list bool, list char, etc. So, list A stands for lists whose elements are of type A. Okay, good. So, that is a generic list. Here are some example polymorphic functions on list. Head, its type is list A arrow A. Length, its type is list A arrow int. Reverse, its type is list A arrow list A. Take, its type is int arrow list A arrow list A. We have seen many other examples as well. We saw, for instance, map. Its type was A arrow B arrow list A arrow list B. In fact, we can open a new page and write out. Yeah, the important thing is that all A's in the type must be instantiated in the same way. So, you can have take an instance of take which can be given type int arrow list char arrow list char. You can have take 1, you can have take 2 whose type is int arrow list bool, but you cannot mix it up. You cannot have a take 3 whose type is int arrow list char arrow list bool, because one A is substituted with by char, another A is substituted with by bool. Okay, this is wrong, not allowed. Okay, good. So, let us write some more functions of these polymorphic types. Map, which we have seen already, is of type A arrow B arrow list A arrow list B. Filter, which we saw, was of type A arrow bool arrow list A arrow list A. What else? Take while, A arrow bool arrow list A arrow list A. Split at, int arrow list A arrow pair consisting of 2 lists, each of whose elements are of type A. Okay, and so on and so forth. You can have lots more. Fold L and fold R was what we looked at in detail. Fold R is of type A arrow B arrow B arrow B arrow list A arrow B. Fold L is of type B arrow A arrow B arrow B arrow list A arrow B, and so on and so forth. So, you can have lots of such higher order functions, but all of these are generic in the sense that it does not matter what the underlying list, the type of the values of the underlying list, it works uniformly over all lists of all types. Okay, so that is the point about polymorphism. Okay, so let us move on. So, we have seen reverse, length, etc. are polymorphic. Can we also think of sort as a polymorphic function? Because no matter what you want, sort 3 1 2, you want this to become 1 2 3. Sort of true false you want this to be false false true true. Sort of, let us take Suresh, you want this to be whatever the sorted order is. EHRSSU. Yeah, so this is the kind of thing that you want. Notice that you want sort to work no matter what the underlying type is. You want sort to work on any list whatsoever, no matter what the underlying type is. And the same sorting, in principle, the same sorting algorithm should be used, right? Same sorting algorithm program, let's say, no matter the underlying type. So it makes sense to think of sort as type, having type list A, arrow list A. But there is a problem. Point is, can we sort lists of any type whatsoever? Here is a type which it is not easy to think of how to sort it. Suppose I have an input list of functions +1 star 2 square, I don't know, think of any other function, yeah, 5 minus. How do you compare these two functions amongst each other? Okay, it's a little, or you can even think of other functions, right? Factorial. Fibonacci. How do you compare these functions, right? So one way you can think of mathematically is that, so thankfully these functions all have the same domain and same range. So you can say for all x in domain of f equals domain of G, f of x is less than or equal to G of x. In that case, you can say f is less than or equal to G. F is less than or equal to G if and only if for all x in domain of f, which is the same as the domain of G, f of x is less than or equal to G of x. Okay, this is a definition that you can give. But what is the problem with this definition? The problem with this definition is that you cannot compute f over all x's, okay, to do a comparison between f and G. Yeah, so here is the example in factorial +3 star 5. How do you compare f less than G for functions? You might yeah, so you might want to say for all x in integers or in but there is a problem, because take factorial for instance. Factorial, if you define factorial in the naive manner, factorial -1 does not terminate at all. If you try to start the computation, so only if factorial -1 the computation terminates, you can check whether factorial -1 is less than +3 applied on -1, right. So in order to be able to do this check, you need to compute both the functions, and you might have functions that are not defined over all of their inputs, and even if they are, it will be highly costly to compute this function over all ints or all integers. At least here we said int arrow int. If we had said integer arrow integer, you would have to compute f on every integer value, which is like, I mean, it is just the bounds of your memory, right? It is not even like 64-bit or whatever. So it's infeasible. So therefore, functions cannot be compared. Haskell compare functions with less than. For the same reason, it can't compare functions for equality. Because what is the notion of equality of functions? Once again, f equal to G if and only if domain of f equals domain of G, and for all x in domain of f, f of x equals G of x. right. So, to check whether two functions are equal, you would actually compute it on all arguments and check whether the same result is produced. It's infeasible, right. So, Haskell cannot compare functions with less than or with equality. So, therefore, you need to have a way to say that this function sort does not work over all possible underlying types, but only for certain types. How do you specify which types these are? Okay. So, you want to assign a type of the which looks like list A arrow list A for sort, but you cannot, you can only do it provided you can compare the values of type A. Provided we can compare values of type A, then you can give this type, okay. And you need to have a way, to specify this, and that is where type classes come in, okay. Type classes, think of it as a set of types that share common features. Okay, type classes are sets of a type class is a set of types that share common features. For instance, the common feature could be comparability. You can compare between two elements for less than, greater than, or it could be you can compare two elements for equality. Okay, so these are all features. So all the basic types that we know, char, int, integer, bool, string, double, etc. You can compare for equality, right. So, that is a common feature that all these types have, but there are some features that only some of these types have. For instance, integer, int and double, the operation plus makes sense, because these are numeric types. So, you can add, you can subtract, etc. But even here there are certain things which make sense only for integer. For int and integer you might do div mod, for double you will do slash, right. And you can do arbitrary division in this thing. You can take reciprocal by doing 1 divided by x. You can do such things here, but not in int or integer, okay. So, there are certain types which there are lots of ways in which you can group together types, okay, and this kind of grouping is called type class, okay. One way of grouping is to say, okay, every type that admits an equality check. Another this thing is to say, oh, every type that allows less than, greater than, equal to comparisons. Another thing is everything that allows plus, minus, etc. So, we will see a few of these type classes, okay. So, type class is a collection of types with a required property or with a shared property. So, in our case, we have this particular type class called ORD, okay. Think of it as orderable elements, elements which can be given an order, which means that between two elements you can compare and say which is smaller and which is larger, or whether they are equal, okay. So, ORD T is a predicate that evaluates to true if T belongs to the type class R, but you do not use ORD in programs, you use ORD only in types, and the way you will specify it is to say ORD A implies list A arrow list A. That is the type of sort that you would give, okay. So, when you want to spell it out, you will say there is an ORD instance of type, or alternatively T is an instance of ORD. This is better. You can say therefore that yeah, for instance, you can apply sort on integers. Int is an instance of ORD, whereas int arrow int is not an instance of ORD, okay. Okay, so what is the shared characteristics? What is the characteristic shared by all types that belong to the class ORD? It is that elements of T can be compared using all these operators, less than or equal to, greater than or equal to, and slash equal to. Okay, this is ORD. So for T, okay, so for T to be an instance of ORD, it should also be an instance of EQ. EQ allows elements to be checked for EQ and not equal to checks. Okay, so if T is an instance of EQ, then equal to and not equal to are defined for T. If T is an instance of ORD, then less than or equal to, greater than or equal to are also defined for T, in addition to equal to and not equal to. So in a sense you might say that ORD is a subclass of Q, but this is not to be confused with your object oriented programming notion of class and subclass, etc. In fact, actually if you look at all types, when ORD is a subclass of EQ, it means that ORD has more features than EQ has more features than. So it means that if ORD T, then EQT, which means that if you consider the collection of all T types T such that T is a type that will actually be a subset of the collection of all T such that T is a type. Okay, so you have this notion of subclassing, but we won't be using this notion of subclassing in our Haskell programs. We will just be using type classes in this sense that when you need to specify a type, you will specify it like this: ORD T double arrow greater than, and then you will say list T arrow list T. Right? This is all we will be doing with type classes, but it is very good to know the common type classes. When you get to advanced Haskell, you might see how you can create your own type classes. We may or may not look at that later, but you absolutely need to be comfortable with how to use type classes and the more common type classes. Okay, so what you will do in the rest of the lecture is to look at a list of the more common type classes. So let us get back to sorting. The correct type that you would give to sorting is by using what is called a class constraint. You are saying sort can be given type list A arrow list A provided A belongs to the class ORD. Okay. Sort can be typed as list A arrow list A provided A is in the class ORD. Okay, so let us look at more examples. Element, okay, this is the code. Elim x empty list is false. Elim x y colon y is x is equal to y or elim x y. Okay, if x is equal to y, you immediately return true. Otherwise, you go and check whether x is an element of y. What could be the type here? Notice that we are using the equal to symbol here. So elements of, so clearly you don't want, you want to be able to check whether true is an element of false, true. At the same time, you want to be able to check whether A is an element of the string LeBron James, right? And you would like the same code to work in both cases. In fact, this code doesn't matter what the underlying types are, the type of the underlying elements are, provided you can do this equality check, right? So the correct way to give a type for elim is EQA implies A arrow list A arrow bool. Once again, not every type belongs to the class EQ. For instance, the class int arrow the type int arrow int does not belong to the type EQ or ORD or any of these things, right. So, how do you evaluate LMF of func list? You will have to check whether a given function is actually equal to the existing function, and notice that you won't be given a name, right. I might be given an alternative description of f. I might check something like LM I do not know, plus 5 composed with minus 2. So, that is the function. I might want to do a check like this, right. Plus 5 composed with minus 2 is nothing but plus 3. We know that, but you do not expect Haskell to do all this mathematical reasoning inside it, right. So, notice that the names are different, but the table of input output is the same. That is what you mean by equality of functions, right. For all x, plus 5 composed with minus 2 applied on x is the same as plus 3 applied on x, but this is a simple mathematical identity, but Haskell does not have a proof engine built into it, okay. All Haskell can do is to compute. So, you do not expect Haskell to be able to check whether two functions are the same. And in fact, there is a problem because you might have functions that do not terminate on some of the inputs, right. Because there is the possibility of non-termination, you cannot do equality check on functions, right. Right. So, this is the point. Can we check f equals g for all functions? F of x equals g of x for all x is the mathematical definition. This is the mathematical definition of f equals g, but you can't use that in a programming language. So, yeah, and we saw the factorial example earlier, right. So, not all types admit an equality check, that is the point. So, for LM you have to say EQ is the type class constraint that you put for LM, okay. LM is of this type, EQA implies A arrow list A arrow bool. Now, here is the nice thing, Haskell does two things. Firstly, it declares lots of built-in types to belong to various classes. So, for instance, EQ int, EQ char, EQ bool, etc. But it also declares ORD int. That is clear because you will say minus 2 is less than minus 1, less than 0, less than 1, less than 2, dot dot dot. It also says ORD character. How do you compare between two characters? Comparison between two characters based on their position in the character table. Remember that all characters are stored in one big table, and based on the position in the character table, you compare characters. How do you compare bool? There is ORD bool also. Okay, this is the nice thing. Haskell defines these types. Bool is supposed to have two values, false and true. And the way Haskell does it, it orders, it first mentions false and then true. So, therefore, false is less than true. Okay, we will later see how you can define your own data types, and depending on the order in which you define the values in the data type, the ORD instance is defined based on that. Okay, so this is something that Haskell does. Lots of built-in types are already made to belong to various classes, but Haskell also does the following. It says, if you give me two types EQA such that A admits equality checks and B admits equality checks, then Haskell automatically declares various other types to belong to the equality type class. the pair AB, yeah, the pair type, the first component being of type A, second component being of type B. This is the pair type. A cross B you would write, right? List of, so if A admits of an equality check, list of elements of type A also admits of equality check. How do you check whether two lists are equal? X1 followed by X2 followed by dot 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 Xn followed by empty list is equal to Y1 followed by Y2. Yeah, so in fact you can actually write a function for it, right? A Haskell code for it. Rather than writing it in this notation, I can just write Haskell code for it. Or equal, let's say, empty list equals. So if one of the things is empty list, you check whether the other is null. If you have excess here and then y is null, then you check whether excess is null. Depending on whether it is null or not, you will return the value true or false. And if you have r equal of x colon x's on the one hand and y colon y's on the other hand, the check will be x equal to y and r equal x's y's. Okay, so this is the point, right? And this code Haskell automatically writes, and whenever you have some type belonging to the equality type class, the corresponding list type will automatically be placed in the equality type class. Okay, and similarly list of A, etc., etc. Okay, so this is something that Haskell does. But you cannot extend EQA, EQB to EQ of A arrow B, because that is a function type. Okay, this Haskell does not do it for you, nor can you do it, because as we said, in general this problem is hard to solve, right? Okay. So similarly, the class ORD, if ORDA holds, if A belongs to the class ORD, then less than or equal to, greater than or equal to, and not equal to are all defined for A. All these functions will have type A arrow bool. Okay, so this is the point about ORD. The nice thing is that once you have once a type A belongs to the type class ORD, you also can define some things are automatically defined, min and max. Okay, you can define min on your own, but there is an automatic definition provided. Okay, min of xy is if x is less than or equal to y, then x else y, right? Rather than writing this code, rather than forcing you to write this code, Haskell automatically provides this definition. Okay, min, max. Okay, fine. And if A belongs to the class ORD, list of elements of type A also belongs to the class ORD, and you compare two lists by dictionary ordering. So for instance, 1, 2 is less than 1, 2, 3. Why? Because the length of 1, 2 is smaller than the length of 1, 2, 3. Why? Because look at the first position where the elements in the list differ. 1 is the same as 1, 2 is different from 1. At that point, the first list has value greater than the value greater than the second list. So the first list is deemed to be the larger of the two. This is lexicographic ordering, or how you would how things are arranged in a dictionary, right? So AB is less than ABC AB is greater than AAB. And if A and B belong to the class ORD, AB, the pairs AB also belong to the class ORD. Note that when we say ORD, yeah, so we want it to be totally ordered. So here you will compare the first, so 1 2 is less than 2 1. See, because the first component 1 is less than the first component 2, but if the first components are the same, then you will compare the second component. Okay, this is the point. And as usual, you cannot extend ORD A and ORD B to ORD of A arrow B, because function types, as we saw, it's problematic. Okay. Here is the next class, numeric class, and we already mentioned the sum function. Sum of empty list is 0, sum of x colon x's is x plus sum of x's. And for this function to make sense, x and x's could be any type whatsoever, provided the plus function is applicable to x. Okay. Yeah, sum requires plus to be defined on list elements. So num A says that A is any number and supports basic arithmetic operations. Num is sort of the parent class of all numeric objects. So the correct typing for sum is num A implies list A arrow A. The point being that this is still polymorphic because it works whether you use int or integer or double. You can use a variety of numeric types, but it works for all types. But notice that if you use list of double, your output will be of type double. If you apply sum on a list of integer, your output will be of type integer, etc. You cannot mix and match. Okay, and the type class num is nice because it allows you to do lots of things. Here are a few other things that it allows you to do: plus, which allows you to add two numbers; minus, which allows you to subtract one number from another; 5 minus 2, 2.0 minus 3.0, etc. Star, which allows you to multiply; negate, which takes the negative value. So negate 5.0 will give you minus 5.0. Okay. So negate will take the negative value, abs will take the absolute value, abs of 2.0 equals 2.0, abs of minus 3.0 is also equal to 3.0. Okay. Signum is a function from A to A which gives you the sign of the number. So it if input is negative, signum of x is minus 1 if x is less than 0, 0 if x is equal to 0, 1 if x is greater than 0. Right? Signum is a way that signals what the sign of the number is. Finally, you have a from integer function which converts an integer into your specific type. Sometimes you might not just be able to use an integer where you expect a float. Okay? Unlike in other languages where some automatic conversions happen, here sometimes Haskell expects you to do explicit conversion. Okay? And that explicit conversion from integer to whatever your type is done using from integer. Okay? Okay. There is no division operation because division applies only to double, float, etc., but not to int. For int, mod, etc., you will do division without remainder, right? So you will do integer division. Okay. Fine. Signum tells if the input is negative by outputting minus 1 or 0 or positive. Okay, that's about num. Now, num has many subclasses. One subclass is what is called integral. These are numerical types whose values are integers, and inside this integral you will have int, integer, etc. Okay. Note that integer is a type, integral is a type class. and integer belongs to integral, if you will. Okay. Point is that these are types that support integer division and remainder, and any type A belonging to the class integral has the following definitions in addition to the num definitions. Okay. On top of what num allows you to do, you have div, mod. Okay. Div is the integer division, mod is the integer modulus operator, quote and rem. This is very interesting exercise. Find out the difference between div mod and quote rem. Point being that you can apply this to both positive numbers and negative numbers, and either or both arguments can be negative, and this quote rem and div mod display some differences when you apply them to negative numbers. When either one or both arguments are negative, then there is a difference. Okay. Whereas for positive numbers they stay the same. Okay. And div mod quote rem, which is a combination of these, to integer. Okay. So if you have any integral type, you can go from int to integer. Yeah, there are certain situations when you will, we saw already this to integer because you had this string to num function. String to num, we had declared its type to be string to integer, and we defined it to be fold L of, I have a number n of type integer, I have a C which is a character, and I will take it to 10 times n plus in digit to int, but that will return a value of type int. I need it to be integer, so I will say to integer of yeah. So this is what I will do. Right. So this was the example that we saw. So this is just required to do some minor conversions. Okay, so you have integral values, then you have fractional values. These are, so you can think of numerical as being split into integral and fractional. These are types whose values are non-integral. Okay. Okay. Supports fractional division and reciprocal operator. Right. So you have you have the divides operator here, yeah, 5 divided by 3 will give you whatever it is, okay, 1.666 or whatever. And reciprocal, you can say recip 5 and you will receive 0.2, okay. And then as we know, there are the rationals which involve fractions, but rationals sit inside the reals, which sits inside the complex numbers, etc. So rational, if you will, are one of the simplest of the fractional types. So you can promote a rational value from rational to any other fractional type. So from rational is another function that you have. Okay. And rational is a type which we haven't gone through. You express elements as actual fractions in rational. So 3 percentage 5, some such notation you use. Okay, we will look at it in the demo session when we get there. We will look at rationals and how you convert them to reals, etc. Okay. Okay. So finally, so that's it about numeric types. They are very important, and in the exercises and in the examples we will see how you can play around with these. Finally, we come to two important type classes. One is called show and the other is called read. Show is all types whose values can be displayed, okay, and show is always used by GHCI internally, because when you type an expression in GHCI, what it tries to do is to print it. To print it, it needs to be a string, okay, and so it has to convert whatever expression it has computed to a string, okay, and that is done by the And to be able to do that, it needs to be part of the show class. Okay. So show is any type whose value can be displayed, and as usual, functions cannot be displayed. Why? Because when you say display a function, you mean the actual input output table, not the code or the name. Okay, and you cannot feasibly say, oh, this is the function which maps 0 to 1, 1 to 2, etc., and give it as a whole infinite list of pairs. Okay. For a type T to be an instance of this show with a capital S, that is the type class. Show small s is the function defined on all A belonging to show. Okay, all types A which are an instance of show, you need the small s show function to be defined on it. And what does it do? It just converts A to string, that's it. Okay. So essentially it provides a printable representation of values of type A. And for all the built-in data types, Haskell automatically makes them instances of the expected type classes show, for instance. And once again, if you have show A, then you also have or if A belongs to show, then automatically show AB if A, right. If show A and show B, then automatically show of A comma B, show of list A, show of list of A, etc. Okay, fine. Here are some examples. Show of false will give you the value false. Okay, will give you the string false within double quotes, as you can see here. Okay. Show of the character A will give you the string, and inside the string will be 3 characters. One is the quote, another is A, another is the quote. Okay, the whole quote A inside quote will be shown, which means that A inside single quote will be put inside double quotes. Okay. Okay, actually this is a list which consists of 3 characters. Okay, good. So show of 0 dot dot 9, this list is just inside the string. You will expand. If you use some shorthand notation for list, then it will expand and display the whole list. Okay, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, that's what you will get. So show of character A comma false, you will put that pair inside double quotes. But so clearly you try show of plus, and then Haskell will throw an error at you. GHCA will show this error message. No instance for show integer arrow integer arrow integer. Okay, that's what you will get. Yeah, so I hope the type class show is clear. Let's move to the type class read, which is sort of the opposite of show. Types whose values can be read, that is what read is. Okay. For a type T to be an instance of read, you need a definition for the following function, which is read, which should take a string as input and produce a value of type A as output. Okay. But when you use show, you just said show and gave the value, it produced a string. When you say read, it is not clear what a value of which type should be produced. So when you use the read function, you need to specify the target type unless the context determines what the type is. Okay, we will see examples in a minute. All the built-in data types are instances of the expected type classes like show, read, etc. So you will, it works normally. Here are a few examples. Read within double quote 0, 1, 2, 3, 4, note that you cannot use the shorthand notation here, because then it will try to read it as 0 dot dot 4, that is your string, and it cannot interpret it. You have to give it as the full list. Then if you must say that interpret it as a list of integer, list whose elements are each of type integer. So then you will actually get a value here, which is of type list integer 0, 1, 2, 3, 4. Read the character a comma false, okay, that you put inside double quotes, and you say that read this as a instance of char comma bool, as a value of type char comma bool, you will get this. Read the string false, say interpret it as bool, you will get false. If you say read false and don't give anything, then you will get an error like this, exception prelude.read no parse. This is the thing. You try it in GHCA, you will see that this is what you will get. But you can do something like not of read false, then you will get true, because not is a function whose type is bool arrow bool. So the moment you know that you are applying not on value that is being read, Haskell knows that it has to provide the type bool to read false. So it automatically does that and it produces the value true. But if it does not match, it will again give an exception. So you cannot do not of read ABC, right, because you cannot, what ABC is not a bool, okay. Okay. So this is it about polymorphism and type classes. This is extremely important. Not because you have to do some fancy programming with this, but because every program you write will be polymorphic, and every program will be conditionally polymorphic based on some type classes. So you need to be aware of this, and yeah, so I hope you understood enough. Thank you very much. Yeah, so we will meet in the next lecture with some more new material. Thank you.